Okay, so we've made it to chapter 2, and the topic of this chapter is going to be probability distributions. And so we're going to be talking about some of the really important probability distributions that we're going to be using later on in the book. It's a pretty long chapter, about 60 pages, and about half of it at least is talking about the most important probability distribution, which is the Gaussian distributions in its various forms and doing all sorts of different operations on it. And that's a really important one to study. But we'll also talk about a few others as well. And so I think with the point of this chapter, you don't need to memorize all the different probability distributions. Just remember having encountered something like that, so that when you're faced with problems like in the book and in your own fields, you'll kind of know where to look. Let's say for to use the right prior for a particular data set, the right likelihood models, etc. Okay, so this will just give you kind of a survey of some of the important ones. By no means all of them, but many of the really important ones will be covered here. Okay, so I thought I went through the headings this morning. So I thought we'd first do a little chapter overview, kind of how to organize the chapter and what the topics are going to be, and then we'll quickly skim through those headings ourselves, just to kind of just touch on what they are, and then of course, then in future videos we'll go through everything in detail. Okay, so I think the way to think about what's going on in this chapter is going to be organized by the types of probability distributions, the types of variables we're going to be using. So the very first case is, the very first case is binary variables. So you can think of this, for example, like as a coin toss. There's someone's face on it. So here we've got, x belongs to 0, 1. And this is going to give us, so the distribution that deals with these is called the Bernoulli distribution. And that distribution is just has a single parameter, which is like the probability of getting a heads in that coin toss. And then if you want to work on having, so we're all about doing inference and Bayesian inference, so we need priors. So the prior to use for the Bernoulli distribution is the beta distribution. So that's going to be the prior on the parameter, that single parameter of the Bernoulli distribution. So we'll talk about, let's highlight these. So we're going to have the Bernoulli distribution, and this is going to be for the prior. So that's going to be a very short section. Then we're going to talk about the generalization of that. So now you don't have just two possibilities. You have several discrete possibilities. So this is the multinomial distribution. And you can think of this, for example, as like as a die. So and the problem. Imagine it's not a fair die. So each of the different sides have different probabilities of falling, of showing up. So working with problems like that, and that is going to give us the actually should have written this differently actually. So let me write this as I guess more general categorical variables. So like categorical variables, let's say. And what I mean by that is x is going to be to n, for example. Right, and so now keeping with the pattern of the previous section, so this is going to be determined by the multinomial distribution. So there we have to set probabilities of all of for each of the different categories except for one of them, because the sum has to equal to 1. And the prior for this comes from the Dirichlet distribution. So you can think of these as generalizations of the binary case. So that's going to be a couple there, the multinomial. And then we're going to spend really most of the chapter working with continuous variables. So whatever, and x belongs to in principle minus infinity to infinity. Let's move that down here. So that's, of course, going to be the Gaussian distribution. So we're going to spend a lot of time on that, various operations, probability operations on that. And now the Gaussian has two types of parameters. It has the mean parameters, for which we'll use, I believe we'll be using Gaussian as priors on those. But for the variance parameters, we'll get introduced to the gamma distribution. There will be also some, I believe there should be something called the Wishart distribution, which is a prior on covariances. The student t's distribution will come up when we're kind of integrating out variance parameters. Student t distribution. And then there'll be, I guess it's kind of related. So let's just highlight these. A few distribution like that. Will also be, you can kind of think of the type of Gaussian, I guess you can think of, but distributions on the circle. They don't necessarily have to be Gaussian or even the extension of that. So let's just make them be separate. So we'll give it its own category. Let's say continuous, but x belongs to the circle. So circular variables. So we'll talk about those as well. So that's those will be kind of the big four types of distribution that we're going to talk about in particular, but we're going to spend most of our time is going to be spent on that. And then we finish off the chapter with talking about, so these are all parametric distributions. So they all have parameters like means and variances. So we're going to finish off the chapter talking about non-parametric settings. So for example, when you're going to, for example, fit your distribution by maybe like making a histogram of your data and saying, well, my distribution is going to be determined by whatever my data says. I'm going to split up my range of data into like 10 bins, and the distribution I'm going to put on it is going to be determined by how much of my data falls into each one of those bins. So it's not so much, let me just add a separate page here. So here it is. Yeah, so we'll just have one final section. There will be a short section on, actually before we get onto that, yeah, I knew there was something missing. Okay, so the next slightly big topic is the exponential family. So it turns out that all of these distributions are actually can be kind of subsumed under one family, one important family. And so we're going to just talk about that and how it's parameterized and how to do kind of inference in that, because it kind of captures all of these under kind of one umbrella. And then then finally we're going to talk about non-parametric I guess distributions or estimation or whatever you want to call it. And there's going to be a few methods. There's going to be one. There's going to be doing it with histograms, which we kind of talked about. There's one with kind of kernel density estimation. You can kind of think of that as smoothing out a histogram, sort of in some kind of a principled way. And then kind of nearest neighbor methods. So there, the idea is you have some data set, and now to assign, I guess, probabilities or values to new points, you just look at what their nearest neighbors are in the data set. And we'll just talk kind of briefly about that. So, but I think the important topic is going to be really the Gaussian distribution, and I think especially if you're doing more kind of theoretical things, I think the exponential family is also very useful to know about, and because it just kind of captures all of this, all these different distributions under one framework. So you don't have to like learn, you don't have to learn kind of 10 different things. You can just learn, learn the one in some setting. Great. So that's kind of the overview of the chapter. So now I think let's go and have a look. We'll just have a brief look at what's coming up, and that'll be that. Okay. So binary variables. So the very first section is going to be binary variables. and they're going to be determined by this probability of coming up heads. So let me switch to laser pointer. So there we go. That's what that's about. Bernoulli, the person it's named after, doing kind of estimation with the binary variables. The beta distribution is going to be used to put priors on the parameter of the binary variable, and it kind of looks like it has a couple of parameters A and B, and these have actually they have interesting meanings. So I believe, and he discusses it here, but I believe they're equivalent to. You can't actually see it. Sorry. Yeah, you can't see everything there, but either way, for different settings of the A's and B's, you will tend to favor some values of mu over others. And I believe A, you can think of this as kind of an effective number of heads, for example. So here you've had twice as many heads as tails, so your kind of prior on mu tends to be towards a high value, etc. But it's quite flexible. So we'll talk about that. Multinomial variable. So this is now when there is multiple options, so multiple values, like the sides of a die. Continuing on, and the Dirichlet distribution is the prior on, for setting the prior on those parameters. Going on, so this is again kind of the very similar diagrams to what we saw for the beta distribution, but now there's 3 or 4 or 5 different kind of corners. They're kind of let's say 5-dimensional. So you get slices of these presumably would look like the beta distribution, but we'll see. I'm just guessing there. And then we're going to get to like the star of the show, which is the Gaussian distribution. We're going to talk all sorts about this. So he's going to spend a bunch of time just talking about the geometry of this, which is really important. Different ways of characterizing the covariance parameter, etc. What it actually means. This is really important. Kind of the geometry situation is really, really important. What it means. Great. Going on. And then various operations. We're going to do like conditioning one Gaussian and conditioning Gaussians. I think conditioning one Gaussian on another. Things like that. We'll see what we get to. Marginalizing Gaussian distribution, so integrating out. You have a joint distribution which is Gaussian. Now you want to marginalize out some to like leave just x of a. So you've got p of x, a and b, and you just want to leave x of a, so you have to integrate over b. And then so with the Gaussians, they're actually simple formulas for what the answer is. So you don't have to go through these steps yourself each time. We just kind of work out what they are. And I believe this will all culminate into Bayes' theorem for Gaussian variables. So it's all because one of the reasons why the Gaussian is so useful is because all these operations are very tractable. So Gaussians, if Gaussians are going in, Gaussians will come out, and then all of your probabilistic manipulations are just about updating means and variances, which can be really useful and give you lots of analytical insight and also implementation help. So it's just good to know what they are, so you don't have to work out these computations each time. And often I find actually the way the variables update is actually really meaningful and can be insightful, even in settings where the distributions aren't Gaussian anymore. You can kind of think about the Gaussian case and then be like, oh, like what happened there, and that'll give you some insight into what's happening in the situation you're dealing with. Okay, so this is the big summary of that section. So if your p of x looks like this and your likelihood is that, then what happens if you want to like marginalize out y? What is y in terms, this probability of y? It's still normally distributed, but how is it related to all of these different parameters? So here it is, and here's for example the posterior on x given y, and it looks like that. So again, you don't need to necessarily memorize these, but just know that when you're dealing with Gaussians, all of these probability operations give you Gaussians at the end. So all you need to know is what the parameters of those Gaussians become afterwards. And then we go on to maximum estimation. So estimating the parameters mu and sigma, and some of them behave the way you would expect. So this is kind of, for example, the empirical covariance looks a lot like the way it looked when you do it for the scalar variables. So you find your maximum likelihood mean, and then you just do you compute the sample covariance relative to that mean. But anyway, we'll get into that sequential estimation. So this is we also call it like online learning. So all of these things, for example, you've got these n examples, right? So, but often in real life, you can't wait for those n examples to come in. How do you update these things one at a time? So you'll have some estimate, and you'll modify that estimate with each arriving data point. So how to do that? It'll have particularly nice forms for the Gaussian because it's so tractable, etc. Yeah. So here's an example. So you've got your previous estimate of the mean, and now you update it with this particular formula with the new data point that's come in. Very cool. So some of that, doing inference, so getting posteriors on things. Good. Yeah, here we meet the gamma distribution that's going to be used as a prior on the variance, I believe. Let's keep going. This is the Wishart distribution, so the prior on covariances. A student t distribution, so I believe he introduces it in the context of integrating out a variance parameter. And that has interesting properties. It has, for example, heavy tails, much heavier tails than the Gaussian distribution. And the Gaussian distribution, I think by definition, doesn't have heavy tails. But yeah, just so that's that. Periodic variable. So this is important if you're working with, for example, let's say data that's angular, so that has to do with direction on the compass. Like, for example, which way does the wind tend to come from? Then the Gaussian isn't always the right thing because the Gaussian goes all the way out to infinity. So what's the distribution to use? The one that's typically used is what's called the von Mises distribution, which I expect will get introduced here. But again, just kind of doing some of those. I believe it'll just going to be like the version of the Gaussian on the circle. So useful if you're working with that kind of data. Going on. Yep. Mixture models. We'll talk about those when we get there. But this is like the exponential family. So this is quite useful because it subsumes lots of different all these individual cases we talked about are actually absorbed, can be all written as members of this exponential family, and has lots of good properties for doing inference and updating posteriors and things like that. So this will be a really useful, especially if you're doing kind of theoretical stuff. It's really good to know about this. So we'll discuss the exponential distribution. There'll be this interesting notion of sufficient statistics come up. So, so for example, when we're computing the means of the Gaussian, it turned out that actually the only bit of if you're trying to figure out what the mean is, you don't need to keep all of your data points. All you need to keep is like their sum, and that will tell you everything you need to know about the mean. So sufficient statistics are essentially that idea, like the functions of your data that that conditioned on which the parameters can be determined. So basically, if you have those sufficient statistics, they're sufficient because you don't need any more of your data. They're essentially summaries of your data that tell you everything you need for your particular estimation problem. So a really cool concept, and we'll talk about it in this section. Conjugate priors, again, this is a really cool thing. It will have come up as we've, I'm sure this won't be the first place that we'll have encountered in this chapter. So the idea there is like when you're doing Bayesian, applying Bayes' rule, you'll have a likelihood that'll belong to some family, for example, a Gaussian, and then you'll have a prior. And if your prior is actually conjugate to the likelihood, then it'll mean that the posterior is also in the same family. So, and I think there are tables saying, what families are conjugate for what. And that can be really cool because, for example, just like in the Gaussian case, then when you do inference, all you end up needing to do is just updating the parameters of that family. So this idea of conjugacy is quite powerful. If you can get it. I mean, I guess in lots of real life examples, you're not going to have conjugate priors because they'll tell you, your situation will, the prior is kind of determined by your problem. So it's not really determined by mathematical convenience. But if you can kind of model it's good to know about conjugate priors because if you can kind of get away with modeling your priors that way, then it can make estimation really much faster, much more efficient, and I think also much more insightful. So we'll talk about those when we get there. Non-informative priors. So what kind of priors do you use when you want to express the fact that you don't know, you don't know anything? So for example, if you have the mean parameter, right, like the mean parameter of a Gaussian. So how would you express the fact that you don't know what that value is? Like, would you put a uniform distribution on it? But if you want to put a uniform distribution, what are the kind of the bounds of that uniform distribution? And as soon as you put bounds on it, well, you're kind of saying that you do know something about it. So yeah, how do you do this properly? It's not like a solved problem, but there are some interesting answers which will be fun to look at. So let's keep going. And then I think the non-parametric method. So the idea is we've been using kind of parametric distributions that have, that are functions of parameters like means and variances, but that in some ways can be quite limiting. I mean, like, life is much more complicated than that. So there are kind of methods that were really coming up actually around the time this book was written, where there's kind of a new version of these non-parametric methods that allows you to fit essentially arbitrarily complex distributions to your data, but that would be fitted to the amount of data that you had. So if you didn't have too much data, then they would, let's say a simple version of that particular family would be fit. But as your data got more complex, and the models would kind of automatically would fit more complicated versions of themselves to your data. We're going to be talking about just some very simple non-parametric approaches here. So for example, histograms, making histograms of the data to fit distributions to it. Kernel density, so this is essentially like I sometimes think of it as just smoothing the histograms, or for every data point putting a little Gaussian on it and then pooling those Gaussians together. So it's going to be that, and then there'll also be nearest neighbor methods. So I think what this is going to be all about is yeah, I'm actually not super sure how we're going to. I haven't used this one in this context myself, so I guess we'll see what that one's about. But again, more non-parametric, so we don't have like one single parameter. It's kind of fitted to your data, and we'll see what the advantages and disadvantages of that are. Very good. So yeah, again, so it's a bit of a long chapter, and it's kind of going through some of the machinery again we'll need later on in the various chapters in the book. But I think a good one to know about. Remember, you don't have to memorize these things. Just kind of get familiar with them. Get familiar with the processes of like going from priors to posteriors, conjugate priors to make things behave. The exponential family to kind of capture, when you can, because it has all sorts of nice properties. Yeah, and yeah, I think so. I think it should be quite interesting. And then in chapter 3, we'll finally start doing our first, I guess, machine learning proper. But again, this will be another, hopefully, a fun chapter, and at least you'll learn a few things. I know I will. I know some of these topics, but others I don't. So we'll be learning a lot of that together. That's great. So yeah, I hope you found that preview of the chapter useful. Let me know what you think in the comments, and yeah, we'll start with section 1 about the binary variables next time. So hope to see you then. Thanks.